In this video, we're going to take a look at the law of conservation of energy, which states that energy cannot be created nor destroyed. And here's the problem that we're going to look at. So we have here an immovable wall. Attached to it is a spring, which has a spring constant of 50 newtons per meter. And on the end of this spring is some box or block with a mass of 10 kilograms. This block is not attached to the spring. But what we're going to do is we're going to compress this spring and let it go. And we want to see how fast the block is moving when it leaves the spring. Now, one piece of information I left out of here is that it's going to be compressed a distance of 0.2 meters. So let's call time 1 when the spring is compressed. At time 1, we're going to look at all the energy that the block will have. So we're going to look at gravitational potential, elastic potential. I'm going to use S for spring, so spring potential plus kinetic. So the sum of those three things at time 1, which is when the spring is compressed, is going to equal the sum of those three things at time 2, which will be right when the spring reaches its maximum elongation, right when the block leaves the spring. All right. Now, I think we can see that when the block is here and when the block is here, the height hasn't changed. It's on the ground. So in both cases, the gravitational potential energy is 0. When the spring is fully compressed, the block is not yet moving. When it reaches its maximum elongation, it no longer has elastic potential energy. So, the elastic potential energy, when it's fully compressed, is going to equal the kinetic energy right when the block leaves the spring. So, elastic potential energy is 1/2 kx squared. Kinetic energy is 1/2 mv squared. And we want to find how fast the block is moving. So, if I rearrange everything here for v, multiply both sides by 2, divide both sides by m, take the square root, plug in the numbers, so k is 50 newtons per meter, right, delta x is 0.2 meters, and the mass is 10 kilograms. All right. Now, I did out all the math, and I got an answer of 0.447 meters per second, right? Which is a small velocity, which makes sense if you think about it. This is not an extremely high spring constant. We didn't compress it extremely far, all right? So it's going to leave at this speed. Now, for part 2, I want to figure out how high does the block travel up the ramp. Okay. Now, there's a couple different ways I could approach this. But what I'm going to do is I'm going to still call time 1 when the spring is fully compressed. Now I'm going to call time 2 when the block reaches its highest point. Okay. Now, like in part A, when the spring is fully compressed, the block is on ground level 0, and it's not moving, so both of those go to 0. When it reaches its highest point, okay, on the ramp, it's long since left the spring, so there's no more elastic potential energy. When it reaches its highest point, the kinetic energy is 0. So, the elastic potential energy when it's compressed is going to equal the gravitational potential energy when the block reaches up here. Now, one important thing that I forgot to mention is that there is no friction, right? If there were friction here, that would change things. We'd have to account for the work done by friction. All right, so The elastic potential energy is 1/2 kx squared. The gravitational potential energy is mgh. We're trying to find h. So if I divide both sides by mg, K is 50. The spring is compressed 0.2 meters. The mass is 10 kilograms, and we're on Earth. All right, now when I did this, I got a very small number. All right, so it's only going to go up like 1 centimeter. Which kind of makes sense because the velocity when it gets to the bottom of the ramp is pretty small.